Hello, my name is Rob Reynolds. Welcome to Business Calculus, Section 4 of Chapter 4. And today we're going to learn about exponential and logarithmic functions. We're going to be looking at sketching natural logs and regular logs. Natural logs are base E, regular logs are base 10. Their graphs are not going to look much different. And we're going to explore exponential functions mostly for natural logs, because in the business world, base E makes a little bit more sense. If you had previous videos, we talked about using PERT for compound interest. That's probably the most common place you'll find it. So again, logarithms, log, have base 10. And the definition I call a fishhook. If you see a log, you can change it to an exponent by doing this fishhook. So start right here, 10 to the b is equal to x. So I'll refer to that as the fishhook, and that's really the definition of logs. So I'll give you some examples of that. If you have a natural log, it's understood that this is base E. So just want to remind you, if I just see log x is equal to 5, doing the definition, that means the same thing as log x base 10. They just don't write that base 10. It's just understood to be there. There are other understood numbers. If I have the square root of x, you know this is a square root of x. There's a little 1 here and a 2 here, but nobody ever writes them, but they're there. So this is really 10 to the 5th is the answer for x equals x. In other words, you could take out your calculator and do the log of 10 to the 5th, and you should get 5. So natural logs have base E, so e to the fishhook, e to the b equals x is the definition for natural logs. And if you previous video, here was the exponential. We learned how to graph exponential functions, and they started at 0a really, but a was 1, so the general form was a times b to the x minus c plus d for exponents. So today we're going to get a general log function. Y is equal to a natural log, I'll say x minus c plus d, and the b becomes the base. And remember, b up here didn't really affect our graph a whole lot because it was the start value. This was the c is the horizontal shift, the d is the vertical shift, and then we looked for 3 decaying factors, a negative x, a negative a, and a b value between 0 and 1. Well, these 3 decaying factors for exponents also work for logs. And notice the base doesn't affect the graph for what I need a whole lot. But what you need to know is if 0, 1 is on the exponential function, then the inverse of 0, 1 is 1, 0. And you literally just, that's what inverse means. Instead of xy, you have y comma x. So logs are inverses of exponents, and that's why we can write any log as an exponent. Remember, the natural log of -1 does not exist because log functions look like this. They start at 1, 0, so there is nothing over here at -1, and there's nothing at 0 because we have a vertical asymptote. So for exponents, we usually had a y equals 0, but for asymptote, but the inverse of a y equals 0 is x equals 0. So now for logs, we have an asymptote at x equals 0. So we'll get to graphing in just a moment. But I just wanted to, oh, there it comes, graphing. So all log functions start at 1, 0. This is a c shift, a horizontal shift, 1 to the left. And there's no d shift. I can even add a plus 0. And then there's no decaying factor, so we're going to have growth. Remember, the asymptote, which was here in blue, actually gets moved over 1 unit. Oh, crud. I thought that was going to work really good. Let me get rid of that blue, and then let me try this. Oh, I don't know if it's worth it, but I could get this line to go like this, and then draw, so the asymptote, which is supposed to be right here at 0, gets moved over 1. That's what I was trying to do, but it didn't work very well. So instead of x equals 0, it gets shoved over 1 to the left as well, and then I can draw in the log function like this, right? I could find other points on this log function, but I'll save that for a later problem. This one we're shifting 2 units to the right, and then this does affect it. It's a vertical shift. Excuse me, not a vertical shift. There's no vertical shift. This is a vertical stretch, so it's just taking this guy and kind of stretching it up a little bit faster. But let's start about the start point again for logs is not like exponents. Exponents usually start here but at 0, 1, but the inverse of 0, 1 is 1, 0. So we're going to start at this 1, 0 and then move this horizontally 2 to the right and then no units up, and the asymptote, which was, do I have to draw that again? Which was at x equals 0 is going to move over here. Don't make me draw it. It was way too much. At x equals 2, and it's just going to grow a little bit faster. Again, the green is just not quite as fast, but well, again, you could find other points, but I'm really looking for a sketch here. And if you have a point and asymptote, and then you could tell me about growth, I'm much more interested in that than what the author does. The author suggests you just plug it into your calculator, go brain dead, and plug in these values. And since it's kind of Halloweenish right now, I thought this is how I feel when you do that, because you're not learning a whole lot. So I'd prefer the method that I'm teaching you. You can see the answers are the same. Here's that 3, 0. Here's the asymptote, and you've got growth. But I'm not a big fan of just plugging in to your T-chart and graph and plotting points. We're going to learn all of these properties. You can see by the definition a to the 0 equals 1. This is really handy for finding other points on the graph function. If you have the log of 5, base 5, I want you to know that that's a 1 because of the definition. 5 to the first equals 5. This is a really important definition here because you can actually take that x and dump it out front, which we'll learn about the third property of logs. And so that becomes x log a base a. But log a base a we just learned is 1, so that's x times 1, which is just x. They went through a weird way of proving that, and I would do something different. And then the log of this equals the log of that when this equals that. And the nice thing is all the properties for log logs also work for natural logs, which just means I have base e, all the same properties. So again, let's go back to the graphs. Here's what you need to know. If x is positive, it starts at 1, 0. If x is negative, it's going to reflect and about the y-axis and go through the point negative 1, 0. But you can see this x is positive, so I'm going to erase what I did. The start value here, since x is positive, is going to be at 1, 0. I'll do an open dot. This is going to go 4 right and 1 up. The asymptote, which starts at x equals 0, gets moved 4 right. So instead of here, it's 1, 2, 3, 4. And there's no decaying factors, so I would give you growth. So if you can get that point, so let me show you where this 3 comes in handy. If you could get this to say, verify another point, if you could get this to say the log of 3, 3, then that would be a 1 plus 1, and then that would be your y. So 1 plus 1, y would be a 2. But we need to force that to be a 3. So I'm just going to set x minus 4 equal to 3, and I can have that happen when x is 7. So I think I found a point. When x is 7, y would be 2. So 1, 2, 3, 4, 5, 6, 7. Y is 2. You can see I'm off just a little bit. So the log function does not grow very fast. So it's more like blue. Do you see how I found that point? I'm going after this log 3, base 3, and forcing it to be a 1 to find another point. You can't always do that, but it's helpful when you can. This one has a negative out front, so that just causes decay. That's one of the decaying factors, a negative x, a negative a, and a b value between 0 and 1, just like for exponents. So go back and check out how to graph exponents if you haven't already. So this doesn't have a negative x, so start at 1, 0. Go 4 to the left this time. 1, 2, 3, 4. 1 down. There's that point. Instead of at x equals 0, I'm going to go 1, 2, 3, 4 to the left. So the asymptote's not at y equals like my exponents, but x equals -4. And then instead of growth, I've got a decaying factor, one of them. If you have two decaying factors, it goes back to growth. So one decaying factor means decay, so I'm going to start up high and head down low. If you want to find one more point, I think I could do the exact same thing I did before. Let's look for negative log 3 base 3 minus 1 to equal y, which would be y would be -1 minus 1, or y would equal the -2. So now I'm going to try to force this guy once again to be a 3, and I can do that just by setting up x plus 4 equaling 3 and x equal -1. And there's my point. -1, -2, and let's see, -1, oh, I did better. -1, -2. So again, use your graphing calculator to see if you can graph it, but I'm more interested in you not using your graphing calculator. I want you just to visualize this and say, oh yeah, that's going to go left 4, down 1, and I can see that that's going to cause decay. I have plenty of graphs that you can try on this. Remember, this is a decaying factor, the b value between 0 and 1. So try this, pause the video, go to Blackboard, print these things off, and practice drawing these things. I have several examples. And if you have any questions over any of these, oh, there's a negative x1. So now I'm going to start at this -1, 0. Don't move left and right, because it's really negative log base 2 of negative x plus 0 or minus 0, it doesn't matter. But don't move left and right, but go up 1. When I go up 1 for the vertical asymptote, it's also at x equals 0, so it still stays. And this means I have a decaying, so I have two decaying factors, a -a and a -x. So that's going to be growth through this point. And students usually have a hard time visualizing growth through the point. So remember, growth, you read a line like you read a book, or you read a graph like you read a book from left to right. So from left to right, you start low and then you end up high. If you wanted to find that other point, the negative log 2 of, I'm going to have to get this to be a 2 in order to get that to be a 1. Plus 1 will equal y. So I'm going to force this negative x to be a 2, and that happens, negative x equals 2 when x is -2. Let's solve for y. Y is -1 plus 1 when y is 0, so -2 comma 0. I missed it this time, so you can see it. Maybe it looks a little bit more like this. So again, you'll get a little bit more accurate if you use your calculator, but I'm not interested in that. I'm interested in, I don't think this graph, I mean, if you were to graph this graph doesn't really go down that low. It really kind of almost levels off, but it never does. It goes to negative infinity, but it looks really flat. So there are infinitely many, way too many examples, but when I teach this in class, I usually have students try one at the board, and so I have plenty of students and plenty of examples. Here are some properties. For this says the log of a product is the log of A plus the log of B. The log of a quotient is the log of A minus the log of B, or you could use U and V. I usually use A and B. And this is that dump down property, which I kind of mentioned a little bit briefly before, but you can dump that exponent down up front and make it N log U. And the nice thing is all those properties, once again, work both for logs and for natural logs. Another nice little property, remember, you can dump this down out front and become x natural log of e, and the natural log of e is a 1. So that's x times 1, which is just x. So just get to know that. Since logs undo exponents, that kind of makes sense to me, because you've got the log and you've got the exponent, and that's the same thing here. E to the natural log of x, you've got an exponent and a log all together in 1, and so the answer is just x. It's kind of like taking x plus 5 minus 5. If they're really inverses, you should just get back to the original function. So keep in mind these definitions, those inverse properties, because logs really are inverses of exponents. So this answer, if you dump this out front, is the square root of 2 natural log of e, and the natural log of e is a 1. Why is the natural log of e 1, you may ask? This answer is the square root of 2 then. The natural log of e equals 1 because the base is e, and e to the first equals e. So I know that the natural, you could type it in your calculator, but I know the natural log of e does equal 1. Just incidentally, the log of 10 equals 1, the log of 100 equals 2, and the log of 1,000, you guessed it, is 3. However many zeros are, that's the answer. So what would be the log of 1? Yeah, 0. And the log of a negative is undefined. So you can see however many zeros there are for log, that's base 10, then that's the answer. But for natural log, we're looking for natural log of e to be a 1. So this guy, the answer is just going to be 3x because the log will undo the exponent. Again, these are the products, are the properties, 3 properties. If there's a product, you add. If there's a quotient, you subtract. And then I call this the dump down property for the exponents. So for this one, we're going to rewrite this as a sum or a difference, and this will be the natural log of 10 minus the natural log of 9. This one I'm going to change this to an exponent first by writing this as x squared plus 1 to the 1/2. Use the dump down property first, so it's 1/2 natural log of x squared plus 1. And there comes a trap because I just got done saying when you add, then you multiply. But I should add on here, there's a nothing rule. The nothing rule is the natural log of x plus y. That's nothing. You can't do anything with the natural log of x plus y. And that's what I have here, the natural log of, a lot of times students want to say, oh, that's the natural log of this plus the natural log of that. And that's not true. So just stop there. This guy, whenever you multiply, you add, and when you divide, you subtract. So I'll just write it out. Log of x plus the log of y minus the log of 5. This one's a little bit harder because I've got a lot going on here, but it's the natural log of x squared plus, because it's a times right here, the natural log of x plus 1. Remember, this right here is nothing. We can't do anything to that. But for this guy, we can do the dump down property. So it's 2 natural log of x plus that. Let's see if the author agrees with me. Here's part A and part B. I don't think I got, did I get that for part B? Yep, I did. And then C, yay, and that looks familiar. And this one was a tough one, but I think we did that. Right. Condensing, this is going to go the opposite direction, so I would use the dump up property, the natural log of x plus the natural log of y squared. And if I add, then I multiply those, the natural, to write that as one log, the natural log of xy squared. Again, dump up, so the natural log of x plus 2 squared minus the natural log of x cubed, dumping, I don't like red, let's change it to blue. So this is the log of this stuff minus that stuff, and when I subtract, it's the log of a divided by b, and I'll put parentheses around it so you know it's just one term. So I came up with an extra example that's not on your handout because I just wanted you to see what happens when I subtract and I subtract. I just want to remind you, if you have like 5/4 and you divide by 3, that's the same thing as taking 5/4 and dividing by 3, so it's really 5/4 times 1/3, and notice I just take 5 divided by both of those, and I'll say 12. So that's what's kind of happened here. It's the natural log of 5 divided by 4, all divided by 3, which is the same thing as the natural log of 5/12. I think that's right. And of course, there's no solution for that because I just made that problem up. There it is again. I mean, I suppose we could do it step by step. This is the natural log of a divided by b, and then I'm going to subtract the natural log of c. And that means the natural log of this a divided by b, all divided by c. And so the hard part is, well, what do you do with that? It's called a compound fraction. So that's a divided by b divided by c, which is a divided by b times 1 over c, which is that natural log of a. So you can just see, I just multiply those together. If you divide and divide, they're both in the denominator. And that's a nice rule. Whenever you subtract, you put it in the denominator. There's another subtract. Put that in the denominator. So that's kind of nice. If you add, it goes in the numerator. If you subtract, you put it in the denominator. That makes it simple. So solving, the book goes into weird rules for solving. I just want you to talk about how you isolate it and then you solve for it. So isolate the logarithm, or in this case the exponent, and then solve for it. So to solve, to undo an exponent, we log both sides. Remember, you can do whatever you want to an equation along both sides. Let's use the dump down method. That's x ln e, and hopefully you know by now the ln of e is just 1. And so this answer is the natural log 5. So isolate it means get it by itself. So the first thing I would do is get e to the 1/10 t is equal to 4. Then I would natural log both sides and dump this down out front. So instead of writing it up here, I'll dump it out front, 1/10 t, and of course that goes to 1 equals the natural log of 4 if I'm natural logging both sides. So 1/10 t is equal to the natural log of 4, and I would say t is equal to 10 natural logs of 4. Let's see what the author did. Oh, that's solution A, and A, I think we got it. 10 natural log 4. This one, remember the base is e, so I'll do the fish hook, e to the 5th equals x. And this one, if I subtract off 3, I'll get 2 ln x equals 4, divide through by 2, and remember the base is e, so e squared equals x. So e to the 5th and e squared. E to the 5th, yay, and e squared. Remember, these answers are posted online. On Blackboard. So applications mean you get some word problems. So the first thing here I see is this word compound continuously, and I know that that's my PERT equation for the amount. And it says how long will it take to double? So if my principal is 1, I want the amount to be 2 e to the RT. Doubling. It doesn't really matter. You could have let this be 100, let this be 200, whatever amount you put in for the principal and you double it, it'll reduce to a 1 and a 2 here after you divide. So the next thing is I'm trying to find how long. So I know I'm going to solve for this t variable. So to solve for t, which is an exponent, I need to undo exponents by natural logging both sides. Then I'll dump this down out front, so RT times the ln of e, which remember that goes to a 1, is equal to the natural log of 2. And finishing this off, I'll divide through by r, or take 1 over r, the natural log of 2, to equal the amount of time. So that's your relationship for time. Here's the author working it out. Let's hopefully see. Yep, they got the same thing. So from this result, you can see it's proportional to the interest rate. I have several other problems. Well, this is the graph of it. Oh my gosh, they're going to go and show you at different values how to make it proportional, and then you could graph it and see what's happening with this rate to finish this problem off. I have several more examples. I would encourage you to work out problem number 40. I've got worked out solutions here. It's very difficult. 46, this is just straight out of your book. I would encourage you to work those out. Here's the worked out solutions. And pause the video here and see if you can solve for x on problem number 64 by adding 5 to both sides first, then dividing by 2, then natural logging both sides. Here's worked out solutions. So pause the video and see if you can't work those out and get the correct answers. If you have questions, email me.